The ideal gas law. Okay, this gas law is a little bit different. You can actually combine Boyle's law, Charles' law, and Avogadro's law into one gas law, and it's called the ideal gas law. If you're interested in how those combine, I'd be happy to show you. But there it is. PV equals nRT. Some people call it PIV-NERT. That's a really important equation, PV equals nRT. So in this equation, we have pressure, we have volume, we have N, and we have T. Those are all variables we've seen before. Now we've got this new letter in here, R. R is a constant. It's called the ideal gas constant. It's the constant for the ideal gas law, so we called it the ideal gas constant. And this is its value. R is equal to 0.0821, and it's got crazy units. Liter times atmospheres divided by moles times Kelvin. You don't have to memorize this, so I'll give that to you as well. But you need to know that you should go look for it. These units tell us what the units on the other quantities have to be. So in the ideal gas law, it does matter what all the units are. Because if we don't match up with the units in the ideal gas constant, then the units aren't going to work out and things are going to be all screwy. So we're going to have pressure in atmospheres, volume in liters, amount of gas in moles, and as always, temperature in kelvins. This is a summary of how these different gas laws relate to each other. I'm not going to talk about it. Okay, so here we have an ideal gas law problem. Calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atmospheres and a temperature of 315 Kelvin. What's different about this problem is that there's no mention of things changing. There's no mention of heating, cooling, submerging, expanding, compressing, nothing like that. So if you read the problem and recognize that nothing's changing, you can go straight to the ideal gas law. But I'm guessing that some of you are looking at these problems and you're finding them to be a little overwhelming. So I'm going to show you that we can still approach this by making a table, and it's not going to waste any time. So we're going to pretend we don't notice that nothing's changing, and we're thinking, oh, maybe this is a combined gas law or something like that. So we'll read the problem and we'll make our table just like we've done before. So the first number is 0.845 moles. And what letter do we use in the equation to stand for moles? N. Okay, 0.845, and then we have 1.37 atmospheres. That's a pressure. And then there's a temperature, 315 Kelvin. Oh, hey, it's already in Kelvin. We don't have to change it. I ran out of numbers, and I only have one row filled out. That's what tells me that I use the ideal gas law, because I'm not going to have ones and twos. I'm just going to have values because nothing's changing. But our table isn't wasted. We'll just erase that bottom line and the first column with the numbers and pretend that we planned it out like this all the time. We have now labeled our numbers. We have N, we have P, and we have T. We need to use the ideal gas law. PV equals nRT. So PV equals nRT. What am I looking for? Volume. It says calculate the volume. So I need to rearrange this equation and solve for V. This one doesn't have fractions in it. So I'm going to divide by P to get those to go away. And I'm going to divide the other side by P. So volume of this gas is equal to nRT over P. R is the ideal gas constant. R is equal to 0.0821 liters times atmospheres divided by moles times Kelvin. These are the units that I need for all of my other quantities. In this problem, my units are all fine. N is in moles, P is in atmospheres, T is in Kelvin. I don't have to convert. If they gave me the temperature in Celsius, I just need to convert it. Okay, so this is equal to N, 0.845 moles, times R, 0.0821 liter atmospheres per mole Kelvin, times the temperature, 315 Kelvin, and that whole mess, whoops, come on, divided by the pressure, 1.37 atmospheres. Check out the units. A little bit tricky because we've got compound fraction here, but we've got atmospheres in the numerator, atmospheres in the denominator. Here we have moles times this fraction with moles in the denominator, and here we have Kelvin times the fraction with Kelvin in the denominator. And so all those units cancel out, and we're left with the unit liter, which is a unit of volume. So then we get our calculators out, we go 0.845 times 0.0821 times 315 divided by 1.37 equals, and this should have three significant figures. It's 15.951 liters. The digit I'm dropping is 5 or greater, so I round the 9 up to a 10, and that rounds the 5 up to a 6, and this is 16.0 liters. That's the volume of the gas. Any questions? Let's do another one. An 8.5 liter tire is filled with 0.55 moles of gas at a temperature of 306 Kelvin. What is the pressure of the gas in the tire? What law do we need? The ideal gas law. Could you recognize it from the problem, or are you just going from this, where it says the ideal gas law at the top? So we have one volume, we have 1 moles, we have 1 Kelvin. Charles' law, Boyle's law, Avogadro's law, there'd be like 2 temperatures or 2 volumes, right? Here there's just 1 of each. So you can make a table, or you can say, oh, well, I recognize that this is the ideal gas law, so I'm just going to write down what these things are. 8.5 liters, well, that's equal to the volume. And 0.55 moles, that's N, and the temperature is 306 Kelvin, so that's T. When you take your PV equals nRT, this time I'm solving for pressure, so I'm going to divide by volume. Pressure equals nRT over V. N is 0.55 moles. R, 0.0821 liter atmospheres per mole Kelvin. Always write the units. Times the temperature, 306 Kelvin, divided by the volume, 8.5 liters. So the moles are going to cancel, the liters are going to cancel, and the kelvins are going to cancel. 0.55 times 0.0821 times 306 divided by 8.5 equals 1.62558 atmospheres. How many sig figs? 2. So 1.6 atmospheres. Any questions? Sometimes we have to do unit conversions before we can use the ideal gas law. So here is an ideal gas law problem requiring unit conversion. How much volume does 0.556 moles of gas occupy when its pressure is 715 millimeters of mercury and its temperature is 58 degrees Celsius? So this is an ideal gas law problem. We don't have things changing, so we're going to write down what these things are. So 0.556 moles. That's N. Ooh, I should do this the other way. N equals. We've got a pressure of 715 millimeters of mercury. So that's the pressure. And the temperature is 58 degrees Celsius. Well, we've had to convert temperatures before. So we need to put this into Kelvin. So we're going to add 273. 58 plus 273. Yeah, didn't do that right. 331. R is 0.0821 liters times atmospheres divided by moles times Kelvin. N is in moles, so that's okay. The temperature we converted to kelvins, so that's good. Can we use millimeters of mercury? No, we can't. We need to convert it to atmospheres. You can do this in the equation, but I think it's easier, more straightforward to do it beforehand. So I want to convert to atmospheres. I need to multiply by atmospheres, divide by millimeters of mercury. 1 atmosphere is equal to 760 millimeters of mercury. I'll give you that conversion factor, but it'll save you a lot of time if you remember it. And that is an exact conversion. So 715 times 1 divided by 760 is going to be 0.940789. That should have 3 significant figures because the 715 had 3 significant figures. The 1 to 760 is exact. That's atmospheres. It's best not to round it yet. So we've got PV equals nRT. We're trying to find the volume. So volume equals nRT over P. Zero 0.556 moles times R, 0.0821 liter atmospheres per mole Kelvin, times, I didn't leave myself much room, 0.9407889. I don't recommend this. Atmospheres. But that's what kind of a day it is. Divided by, why don't you guys stop me? Because it's fun to watch the teachers screw up. Good grief. Bless you. The pressure goes down here, not up there. Let's have a good eraser. It's the temperature in there. At least that's shorter. It squeezes in better. Okay. An example of why it's important to write this down. You're doing a mastering chemistry problem. You put the wrong answer in. If you haven't written anything down, you have to start over. You might make the same mistake again. If you write it out, you can look at it and see what you did wrong. A lot of times it's something dumb like I just did. Everybody does stupid things. That doesn't make you stupid. I do at least one stupid thing a day. I've already exceeded my quota for today. So we do the math, and I'm getting 16.0603. What's the unit? Liters. So moles canceled, and atmospheres canceled, and kelvins canceled. How many significant figures should that answer have? 3. The number of moles had 3. The pressure had 3. When I converted it, it still has 3. This temperature only had 2, but the conversion involves adding, and so when I convert it, now it has 3 significant figures. And the ideal gas constant, as it's given to us, has 3. So we should have 3, and that's going to be 16.1. Any questions? Yes?
So what happens when they don't give us a mole?
If they don't give you the moles, they could give you a mass of a particular gas. They'd have to tell you what the gas is. They could say, well, what if it's 5 grams of nitrogen? Then you have to take the grams and convert to moles by using the molar mass. And sometimes they'll ask you to solve for the temperature or solve for N, the number of moles. Any other questions? We can use the ideal gas law to find the molar mass of a gas. And we're going to do this in lab. Wait. No, that's another class. Sorry. We're not going to do this. Scratch that. No, we can't. We can't. Sorry. It'd be great if we could skip this. We might finish the chapter, but we can't. So this is how you would go about that. You take a sample of gas, and you can weigh it and find out its mass. So here, this one has a mass of 38.8 milligrams. And we measure its volume, 224 milliliters. Measure its temperature, 55 degrees Celsius. Measure the pressure, 886 torr. And from this information, we can find the molar mass of the gas. So this is not immediately obvious how we're going to do this. Well, let's think about it. What is molar mass? It's the riding lawnmower going past on the sidewalk, because it's important to keep those sidewalks cut down. Molar mass. What kind of units does molar mass have? Not ATM. It has moles in it. Molar mass has moles and grams. Okay, it's the mass in grams of 1 mole, right? So the molar mass, which we sometimes abbreviate MM, that is going to have units of moles, no, not, grams per mole. When we calculate it, we often say, okay, like helium is 4 grams is equal to 1 mole. So if we take the mass and divide by the number of moles, that gives us the molar mass. So what we need to do is we need to find the mass of this sample and how many moles are in the sample, and then we can find the molar mass. Do they tell us how many moles? No. But they gave us a temperature, a pressure, and a volume. PV equals nRT. We could calculate the number of moles based on the volume, the temperature, and the pressure. So the volume is 224 milliliters. The temperature is 55 degrees Celsius. What do we need to do to that? Change it to Kelvin. Kelvin, Kelvin, Kelvin. 55 plus 273. 328. On the multiple choice exams, the incorrect answers are not random. We know what mistakes students make, and so we put those in there. And so there probably will be an answer. If you did everything else right, but you forgot to convert to Kelvin, you will find an answer there that matches what you get. Right? So mean. Pressure is 886 torr. We need the ideal gas law. PV equals nRT. This time we're solving for N. We want the moles of gas. I don't want to put that right there. I want to move it over. PV equals nRT. So we want to solve for N. We're going to divide by R and T. N equals PV over RT. I don't have enough room on this slide. R equals 0.0821 liter atmospheres per mole Kelvin. We need to make sure that our units match up with the units on the ideal gas constant. Which ones are not matching up? Milliliters and torr. So we need to fix those. So this is going back to chapter 2 for the volume. I'm going to divide by milliliters and multiply by liters because I want the units to cancel out. What does milli mean? 10 to the -3 or +3? -3. So I've got 1 milli in the bottom. I've got 1 times 10 to the -3 on top. So this is 0.224 liters. Common mistake is students will end up with 224,000 liters. So we have some experience in lab right now, right? So we measure things, you know. How much is a milliliter? Show me with your fingers. It's small, right? It's a test tube about that tall, right? It's a little bitty bit. How much is a liter? It's half of a 2-liter soda bottle. Okay, so which one's bigger, a liter or a milliliter? A liter. So if we have 200 milliliters, the small unit, could it be 224,000 liters? No, that would be a lot of soda bottles, right? It must be 0.224 liters, it's small. So if you think about it, large unit has the small number, small unit has the large number. And then torr, we need to convert to atmospheres. So we'll multiply by atmospheres and we'll divide by torr. And the relationship here is the same as for millimeters of mercury. 1 atmosphere is equal to 760 torr. 886 divided by 760. This pressure will have 3 significant figures. So there's my 3, and then I'm going to keep 2 extras. That would round up to an 8. That would be atmospheres. Now I can plug these numbers into my equation. The pressure, 1.1658 atmospheres. The volume, 0.224 liters. R, 0.0821 liters atmospheres per mole Kelvin. And the temperature, 328 Kelvin. Here again, we've got two numbers that we're dividing by, so we need to be careful. 1.1658 times 0.224 divided by, we decided we're going to use parentheses, open parentheses, 0.0821 times 328, close the parentheses, press equals, n equals 0.009697. How many sig figs should that have? 3. So there's 3 sig figs. I'm just going to keep 2 extras, moles. That's a really small number. Is it wrong? Not necessarily. Just because it's really big or really small doesn't mean it's wrong. Is that our answer? No. This is a big old mess of a problem. Okay, I'm going to change colors because this is getting very cluttered. So this is what we were doing. Molar mass is the grams divided by the moles. Well, we just figured out how many moles are in this sample. 96974 moles. What's the mass of the sample? 38.8 milligrams. Well, that's not going to work, is it? We need that to be in grams. 38.8 milligrams. We're going to multiply by grams, divide by milligrams. 1 milligram is 1 times 10 to the minus third grams. And so this is going to be 0.0388 grams. 0.0388 grams. 0.0388 divided by 0.009674 equals, with 3 sig figs, I'm getting 4.01 grams per mole. Is that a possible molar mass? What's the molar mass of helium? 4.003? That's pretty close. What if I got a molar mass that was 0.5 grams per mole? Is that possible? What's the smallest element's molar mass? Hydrogen. Hydrogen is 1 gram per mole. And that's hydrogen atoms, which do not go around by themselves. That would be 2 grams per mole. So if you get anything less than 2, it's not possible. You did something wrong. Any questions? We'll do that next week.